So in our first few lectures on optimization, we're going to look at some one-dimensional unconstrained optimization. And we're going to start off with bisection methods. And if you recall, in our root finding technique using bisection from what you've learned previously, is that the root finding for a single nonlinear equation, the goal is to find the value of x that yields the result of f of x being 0. Here we have two roots, for example. Now with optimization, the goal becomes slightly different, and that is we are now looking for the value of x that results in finding some general extremum. And we're going to look initially at the golden section search method, which is very similar to bisection, in that this method we define an interval x upper and x lower, and instead of like what we did with the root finding technique, where the presence of a root was denoted by the sign change or difference in sign between fxl and fx upper, so a difference in sign means that the multiplication of the two would be less than 0, and the root was approximated by x lower plus x upper divided by 2, and we keep reducing the bracket until we converge on a root. The golden section method, and we're going to apply it to the to locating a maximum. It's slightly different when we look for minimums. So initially we very similarly define this interval that contains a single maximum. We call this unimodal, and then we use the same convention as the bracketing method, that is, we define x upper and x lower, and instead of using two function values, we will use three function values to detect whether a maximum has occurred. And unfortunately, the downside to this method is that we have to choose those choose these additional points. So for example, if we had x upper and x lower as we have done here, we may define a new interval or additional points. Let's call this x1 and x2. So we select these 2 points. So x1 and x2 are within the interval xl and xu. And we check for a maximum. So either between the 3 points, so f of xl, f of x1, and f of x2. So we search for a maximum between these 3 values, or between f of x upper, f of x1, and f of x2. So you can see how we're using 3 values to search for a maximum. We then eliminate either xl and x2 or x1 and x upper. Now, I've already mentioned that this entire method depends on our selection of x1 and x2, and we need to find an efficient way to do this, and I'm going to show you how to do that in the next video.